Hey guys, welcome back. Today we're going to be starting RLC Series circuits, and I've got an example here that we're going to take up. You already know how to do this because you know how to do RL series circuits, and so this is just another series circuit, but it has one more component. So follows all the same rules that we've been learning about RL series circuits, just has a third phaser. This, by the way, is Unit 4 handout 4, and it is question number 1. We will take up question number 3 as well in the next video, but let's start with this one. So after you flip to it, let's take a look at it real quickly here. Notice that it gives the capacitance in microfarads and the inductance in henries, and whenever you see that, the first thing you're going to have to do is figure out how many ohms those gadgets are. If you don't calculate the ohms, you're not going to be using the right number. So XC is equal to 1 over 2 pi FC. And so I did that math, and it comes to 45.12 ohms. And XL is equal to 2 pi FL, and I did that math, comes to 221.2 ohms. And so what I end up with is this RLC series circuit right here. 45.21 is the capacitor, 221.2 is the inductor, 25 ohms is the resistor. So we're going to solve this. Looks like we need to solve for Z, and Z is going to be, the sum of all the gadgets in the circuit that are limiting current. And in order to calculate Z, I've got to use phasors to do it. We're going to do it the same way as we were doing it with RL series circuit, except for we're going to have 3 phasors. So if we're going to draw 3 phasors, we've got to draw our little phasor world here. And so let's do that for a second. All right, and we're going to compare all our phasors to the current, and I'm going to start by drawing this resistor right here. It is in phase with the current, so it's going to sit right out here like this. R is going to be equal to 25 ohms. Okay. The next phasor we're going to draw is the inductor. Now, it doesn't matter which phasor you draw after you've drawn the resistor. You should probably draw the resistor first. Draw these ones any which way you like. I noticed that I didn't give myself enough room to draw a phasor that's 221 ohms long, but it doesn't matter. We'll, it won't be to scale, or it won't be perfect, but we'll figure it out here. So we'll draw the inductor next. It is 221.2 ohms. It needs to be drawn so that the current is lagging by 90, but I'm going to move it tip to tail. So it's actually going to sit right here, and this is too short, but we're going to pretend that XL here is 221.2 ohms. The next phasor we're going to draw is XC, and XC is 45.21 ohms, and XC causes the current to lead by 90 degrees, which means if I were to draw it where it actually belongs, it's belonging down here, lagging the current, so that the current is leading it or counterclockwise from it by 90 degrees. But I'm going to move it tip to tail, so we would draw it straight down here, 45. I'm going to move it tip to tail, and I'm going to put it right here, 221 up. Now we're going to go 45 down. So this is 45.21 ohms. Now, if you notice that these are 180 degrees out of phase, which means I can just actually subtract these. This here, whoops, we're going to call X, and X is going to be XL minus XC. It's going to be whichever is bigger, it's going to be the difference between these two. So we're going to do that. It's going to be 221.2 minus 45.21. And so X here, that little line right there, is going to be 221.2 minus 45.21. 176 basically. Okay, so we're going to just call that 176 ohms. All right. Now, the phasor sum of the 3 of them is going to be a line that starts at the first one and ends at the end of the last one. So there's the phasor sum of the 3. This is Z. It is equal to 25 squared plus 176 squared square root. So we're actually going to calculate it right here where we have some room. It's going to be the square root of 25 squared plus 176 squared. Let's do that. 25 squared plus 176 squared equals square root 177.8. 177.8 ohms. 177.8 ohms. Okay, guys? So that's the answer for A, 177.8 ohms. Now that we've done that, we can calculate the current in the circuit, and now that I know the impedance of the circuit, I can calculate the current. I is going to be the voltage, E over Z, and the voltage is 100. Z is 177.8. Okay, so 100 divide that, 0.56, I don't know, 3 amps. 0.563 amps. Now it's exactly the same. We are going to calculate EXL, the voltage dropping across the inductor, EXC, the voltage dropping across the capacitor. Oh, EXC is the capacitor, EXL is the inductor. For some reason it doesn't ask about ER, but we could calculate it too. Let's do them one at a time here. So this is A, guys. This is B. Here's C. EXL, well, E is equal to I times XL. So we've just calculated the current. I'm going to get 0.563 times XL, 221.2. 124.4 volts dropping there. That's EX. Guys. EXC. I times XC. 45.21. Let's try that again. 0.563 times 45.21 equals 25.45 volts. 25.45 volts. D. EXL is I times XL, which is equal to 0.563 times 221.2, which is equal to 124.4 volts. Okay, that's the one I should have done there. So this is 124.4 volts. Sorry about that, guys. I make a lot of mistakes. Actually, now that I can watch myself teach, I'm actually kind of horrified at how many mistakes I make. And, I don't know what to do about it. Maybe I should quit teaching or something. I'm not sure. In the meantime, some of them I make and I notice. Other ones I make and I have no idea. And I don't notice until I watch the video. So I feel sorry for you guys having to deal with that. All right. Phase angle, guys. Here's the triangle. Can you see it? So the phase angle is going to be right there. Phase angle here is going to be opposite 176 over adjacent 25. Inverse tan. Let's do it. 176 divided by 25 equals shift tan equals 81.9 degrees. 81.9 degrees. Okay, now hopefully what I did there makes sense. But let's talk about this, leading or lagging, for a minute, because this question is going to come up over and over and over again in the next 5 weeks or whatever. So what does this mean? So the first thing I need to say about this, guys, is that if I'm asking you about a circuit, whether it is leading or lagging, I am asking you about the current. Okay, that is just an industry standard. If you say that circuit is lagging, you're saying that the current is lagging. If you say that the current circuit is leading, you're saying that the current is leading. Okay, now anytime you have something lagging, you also have something leading And so in order to make it like clear across the board, you always talk about the current. All right, so that circuit lags means the current is lagging. So when I'm asking you leading or lagging, I am asking you about the current. Because now I have a circuit here where a capacitor, which is causing the current to lead, I've got an inductor, which is causing the current to lag, I've got a resistor, which, doesn't lead or lag. And so if I looked at this whole circuit, would the current would the current be leading or lagging? Basically is what I'm asking after we're all said and done. Now, how do you decide whether the circuit leads or lags? There's one way that works for every kind of circuit, because we're doing series circuits now, we're going to do parallel circuits soon, and we're going to do combination circuits soon. If you want to know what one rule is for all circuits in order to determine whether they lead or lag, it is you take a look at the phasor diagram, any phasor diagram that is legitimate for that circuit, because there is a voltage phasor diagram for this circuit. We haven't drawn it, but the sum of the voltage drops will equal the voltage rise in this circuit, just like any circuit, series circuit, I should say. So if you happen to have a voltage phasor diagram, you can do it with that phasor diagram as well. But in order to determine whether the current is leading or lagging, you identify the current phasor in the circuit, you decide whether it is clockwise or counterclockwise from the impedance or voltage phasor. Okay, because it depends on whether you're looking at impedance phasors or voltage phasors. You compare the current to the impedance or voltage phasor and determine if it is clockwise or counterclockwise, because clockwise phasors are always lagging and counterclockwise phasors are always leading. And so if I take a look at this current phasor, guys, I'm noticing that it is clockwise from the impedance phasor, and clockwise means it is lagging. Okay, all that means is that in this circuit, if I scope this, I would see that the current was leading by 90. If I scope this, I would see that the current was lagging by 90. If I scope this, I see that the current is phase. If I scope the whole circuit, I will see that the current is lagging by 81.9 degrees. In other words, if I scope the whole circuit, I would see the voltage in this circuit, E, and I would see the current in this circuit lagging not by 90, but by 81. Okay, so the current will look something like this. This being 81 degrees, 0.9 degrees. Okay, 90 being like right there. Right, guys? So that's what it's talking about. It's asking about the current, this pink line, and it wants to know if it is leading or lagging the voltage and by how much. Okay, lagging by 81.9 degrees. Okay, guys? We are going to do another one. I will do it more quickly, I guess you could say, and we'll see how it goes. But stick around for the next episode of Level 2 Theory with Fernando. Have a good one.